System design is not a one-size-fits-all. The scale of your product matters immensely when making design decisions. A blog with 100 users will be built wildly differently to how Netflix handles millions. First, let's discuss what scale actually means. The most common misconception here is that people think scale means users. The issue with this is that not all users are on the same platform. For example, one user on a blog probably only accesses 1 or 2 posts, which only queries the database a few times. But one user on a messaging app would query the database hundreds of times, as they send and receive messages, update statuses, and view typing indicators, all of which require constant, real-time data retrieval and updates. So, if users aren't the right metric for scale, what is? Well, we just talked about it. Queries per second. The primary metric for representing scale and system performance is queries per second, with requests per second being a secondary metric. Of the two, QPS is the more important metric because stateless services that handle web requests are much easier to scale, and databases are often the most constrained part of any system. For this video, we'll be looking at QPS to represent scale. Now, take a wild guess. What website do you think has the highest QPS on the entire internet? Write your answer in the comments and we'll reveal our answer at the end of the video. Now that we've established that QPS is the metric for scale, let's divide systems up into 4 levels of scale and go through each of the best practices for these systems. Small scale is anything that falls between 1 and 100 QPS. The examples that come to mind of this include highly static websites, internal tools, and startups with few users. If you're building something at this scale, the rule of thumb is to keep it simple. Opt for a monolithic architecture and use the simplest tools you can find. A basic backend and frontend framework, SQL database, and a single server is often more than enough. If you have a lot of static content, including a cache is also beneficial, as you can store almost all of your static content in the cache, significantly reducing the number of calls you need to make to your database. In fact, small scale does not mean small revenue. There are many multi-million-dollar companies that have under 100 QPS, purely because they are almost all static content that can be served through a cache, or because the users don't actually frequently query the database. Small-scale systems make up probably 95% of the internet. But if you're preparing for system design interviews, you're likely working at a company with higher scalability requirements. So let's take a look at the next size, medium scale. Medium scale typically falls between 100 and 1000 QPS. At this level, you're likely dealing with a growing user base or a more interactive application, such as a popular blog, a SaaS platform, or a community-driven website. With more users generating requests, a simple monolithic setup might start to show limitations in performance and responsiveness. To handle medium-scale demands, modularity and flexibility are key, so let's cover some effective strategies. The first one is backend architecture. Shifting to a modular or even microservices architecture helps a ton. By separating part of the application, you can scale individual services independently based on their load, keeping the system efficient. Next, let's talk about database optimization. Medium-scale systems often experience more frequent database access, so adding read replicas is common. This helps offload the main database by directing reads to replicas, reducing contention. Caching also becomes essential for infrequently accessed data, with tools like Redis or Memcached used to frequently serve data and quickly relieve the primary database. Next, moving on to infrastructure. To handle increased traffic, horizontal scaling is key. Rather than just one server, you can add servers as needed, distributing requests and improving resilience. Tools like Docker for containerization and Kubernetes for orchestration make it a bit easier to manage multiple instances and keep services running smoothly. And lastly, load balancing is key. Implementing a load balancer distributes incoming traffic across servers, ensuring that no single server gets overwhelmed. This setup also improves fault tolerance, as traffic can be rerouted if a server goes down. An example of a medium-scale system might be a smaller networking app where users regularly like, comment, and post, requiring both high availability and performance. At this scale, you're building for a balance of reliability and responsiveness while keeping infrastructure manageable and costs in check. Medium-scale systems are where many successful applications operate, often for years. If your application continues to grow, however, you'll soon be ready to move into high-scale territory, which is where scaling starts to become trickier. High-scale systems handle 1,000 to 100,000 QPS and are often found in established platforms with millions of active users, like major e-commerce sites, popular SaaS products, or social media platforms that are popular. At this level, the demand on your system is high, requiring advanced solutions to maintain performance, reliability, and scalability. Let's take a look at some of the ways you can do that. Firstly, we're going to take a look at microservices architecture. At a large scale, microservices are 100% essential. Every service needs to be dedicated to a specific function so that it can be scaled independently. This modular approach allows teams to optimize and deploy individual services without impacting the rest of the entire system. Data management is also essential in any large-scale systems. With thousands of requests per second, distributed databases and data partitioning are crucial to handle large data volumes and prevent database overload. Event-driven architectures are also very common, using message queues such as Kafka to manage a high volume of transactions and decouple services. Advanced caching is another strategy you can employ to manage large-scale systems. Heavy caching reduces the load on databases and accelerates response times. Using in-memory data stores like Redis or Memcache are essential for serving data instantly. At this level, you may also use multi-level caching, which is caching at both the database and application layers, to ensure quick access to frequently requested data. Container orchestration is another tactic you can use. Large-scale systems rely on container orchestration with tools like Kubernetes in order to manage hundreds or even thousands of different containers. Once again, load balancing is also essential at this scale, but you will have to start looking at more advanced load balancing strategies and traffic management to ensure that requests are spread evenly across servers, optimizing resource usage. And lastly, resistance and fault tolerance is key. With many interdependent components, fault tolerance becomes critical. Large systems are often deployed across multiple data centers or cloud regions to ensure high availability and reduce latency for global users. An example of a large-scale system could be a popular e-commerce platform like Etsy, especially during a big sale event. With thousands of users making purchases simultaneously, the platform requires a highly scalable and resilient infrastructure that can handle sudden surges in traffic without sacrificing user experience. At this level, every part of the system must be optimized for efficiency and robustness. There are only a handful of companies that will ever need to scale above this level, going above 100,000 QPS. But this is where the most advanced system designers go to work on cutting-edge work, and is what we'll talk about next. Extremely large-scale companies operate at over 100,000 QPS, the level where even minor inefficiencies can cause catastrophic issues. This scale is typical for global platforms like major social media platforms, large streaming networks, or even real-time financial trading systems, where millions of users interact simultaneously. Designing for this kind of scale requires an architecture that can handle immense demand and withstand constant, unpredictable fluctuations in traffic, and not something that can be learned in a short video, let alone years of learning. However, we'll still try to cover some of the essential strategies here so you have an idea of how these massive systems scale. Firstly, globally distributed systems are essential. Data is replicated across multiple regions and continents to keep latency as low as possible and ensure that users receive quick responses no matter where they're located. Distributed databases like Google Spanner or AWS Aurora are popular choices to ensure that data is consistently available worldwide. On a similar note, multi-region deployments are essential. For resilience and speed, applications are deployed in multiple data centers or cloud regions, often across many continents. Edge computing is a tactic that pushes code execution closer to users by using CDNs, also known as content delivery networks, for static content and edge locations for any key computations. This minimizes latency and offloads traffic from core servers. Talking about architecture once again, for massively scaled systems, we take a look at serverless and auto-scaling architectures. To handle an unpredictable demand, many systems use serverless computing, such as AWS Lambda or Google Cloud Functions, that automatically scale with incoming traffic. Serverless functions can expand or contract dynamically to handle surges, helping manage costs and resources efficiently. Multi-cloud and redundancy is another key tactic to employ. With very high scale, reliability is essential. Using multiple cloud providers at once and redundant failover systems ensures that the platform remains available even if one provider experiences some downtime. This approach reduces dependency on any single vendor and improves fault tolerance. Lastly, monitoring and analytics are key for these massive systems. To keep everything running smoothly constantly, very high-scale systems employ advanced monitoring tools that detect issues instantly and trigger automated responses. On top of this, real-time analytics enables rapid decision-making and helps preemptively address any potential bottlenecks that may come up. An example of a system operating at this massive scale is a platform like Netflix, where millions of users are streaming videos simultaneously. The platform relies on global distribution, CDNs, multi-region deployments, and extensive caching to ensure uninterrupted service with minimal latency. Even a momentary glitch can impact millions of users, so every component must be built with resilience and failover mechanisms. Lastly, let's take a look at the question we asked earlier in this video. What website do you think has the highest QPS? Well, there is no one definitive answer, but from our own research and estimates, the highest QPS comes from Amazon, specifically on Amazon Prime Day. In 2021, Amazon released that their Simple Queue service processed 47.7 million messages per second at its peak. Now, it's unknown how many of these messages have queries to the database, and how many queries there even are per message, but the QPS is likely well into the millions, which is an absolutely mind-boggling number. Congratulations, you are now a master of scale. Well, maybe just an apprentice.
Thanks so much for watching this video. If you liked it and want to see more, make sure to subscribe to our channel and hit the notification bell to stay up to date. Also, check out our website at systemdesignschool.io for system design interview practice, complete with an AI auto grader. Thanks, and we'll see you all in the next video.